Hello, and welcome to Lesson 3 of this Introduction to Calculus with Wolfram U. Our topic for today is the elementary functions. So let's begin with a brief overview of today's lesson. So, in the previous lesson, in Lesson 2, we learned how functions can be used to represent change. And we learned how to define a function, plot it, evaluate it, etc. But then we also learned that there are many different kinds of functions. So it's quite puzzling the number of functions that you might see at any one time. So here are a few graphs over here. So let's say that's an oscillating kind of function, and you might have an increasing function or a decreasing function. And the question is, what do you really need to study a calculus in this course? Well, in this lesson, what we'll do is we'll categorize the types of functions that you'll really encounter later in the course. And these functions are somewhat simpler than what you might encounter in advanced mathematics, and hence they are called elementary functions as opposed to what are called special functions. So our topic of today is elementary functions, which we'll study in some detail. So perhaps the simplest kind of function is a linear function. So for example, here is a function f of x equal x plus 3. And if you plot it, what you see is that you get a straight line. So that's a linear function. And in general, the function f of x equal to mx plus b is called a linear function. And that m over there is the slope and the b is the y-intercept. So linear functions are rather simple. Their graphs are straight lines, and they have a slope and a y-intercept, and that's about all. Okay, so to go a step further, let's talk about power functions. So a power function is also very simple. It has the form x to the power a. So here are some power functions with simple powers like 1 and 2 and 3 and 4. Let's plot them. And what you notice is that the graphs depend upon the kind of powers that you have. So if you have an odd degree or an odd power function, then the graphs are odd. So for example, the graph for x is odd, whereas the plot for x square will be even. So these power functions are simple in the sense that the odd degree functions are odd and the even degree functions are even. Now, slightly harder than those are the root functions, where you have things like x raised to power 1/2, like the square root function, basically. And that's just a simple way of saying x to the power 1/3 in the Wolfram language. And those functions are a little more complicated than the earlier set, because now what happens is that if you look at the plots, they look a bit thicker over here than over there. And that's because the odd roots are defined everywhere, while the even ones are only defined for positive or non-negative, really, values of the variable. So here's the square root function, and the square root of a number is only defined if the number is non-negative. So that's the class of power functions which are quite useful in practice. To go a step further, let's talk about polynomials. So that over there, the function f is a polynomial. Now, if you plot the polynomial, you get a graph. It's a nice, smooth graph. And generally speaking, if you want to define a polynomial, you need to set up a sum of this type. So the a's over here are coefficients, while the powers are right over there, n minus 1, etc. And the highest power is called the degree of the polynomial. So this polynomial over here has coefficients 3, -1, 7, and 6, while the degree is 4 because you got x raised to 4 over there. And in particular, linear functions have degree 1, quadratic functions have degree 2, and cubic functions have degree 3. So you have this vast array of polynomials. They are very simple to work with, but they are incredibly useful. So you have linear, quadratic, cubic polynomials, etc., which we'll encounter all the time in the course. Okay, so to go a step further, we can talk about rational functions. So rational function is simply a quotient of two polynomials. It's a ratio of two polynomials. If you divide a polynomial by another, you get a rational function. And perhaps the simplest kind of rational function is the reciprocal function, 1 over x. So if you plot it, you see the plot has got two pieces, and that's because there is a problem at x equal to 0, where the function is not defined. So you have a piece on the right and a piece on the left, and together they give you the reciprocal function. And in general, rational functions are defined everywhere except where the denominators are 0. So wherever the function q over here is 0, you will find that there are problems and the rational function is not defined. But apart from that, they are rather simple to work with, and again, they are incredibly useful in calculus. Okay, so let's go a step further and talk about algebraic function. So an algebraic function is obtained by adding, subtracting, multiplying, dividing, or taking roots. And that, of course, is where all the trouble lies, because when you take roots, you can have all kinds of things going wrong. So here's a pretty complicated algebraic function. It's got square roots, cube roots, etc. in it. And if you plot it, there could be issues. There's an issue over here at 0 because of the denominator, and then the function may not be defined on certain parts. The domain is rather small typically, and these algebraic functions come in a variety of shapes. And although they are interesting, they are somewhat less easy to work with, and we probably will not use them a lot at the start. Okay, so beyond the algebraic functions, we then have the trigonometric functions, which of course many of you might be familiar with. So the sine, cosine, and tangent functions are the trigonometric functions. Now, just a word of warning, in the Wolfram language, we always use the radian measure. So if I say sine 30, that's not so good. You either say sine pi over 6 or sine 30 degrees when you really want the sine of 30 degrees. And then, of course, you get the correct behavior. So the 1/2 over there came out because you use the right notation and the right units. So keep in mind that you must always use the radian measure when working in the Wolfram language, or else you must say degree like I've done over here. So here are the first three plots for trig functions: sine, cosine, and tangent. Okay, and you can see that they are all oscillating, both sine and cosine, and then the tangent function has got these singularities because that's where you have a problem by when you divide by 0, the cosine function is 0, etc. Okay, so those are the sine, cosine, and tangent functions, and sine and cosine have a period of 2 pi, while the tangent has a period of pi only. So they are repetitious and they have periods, but those periods depend upon the kind of function that you're working with. And of course, you've got a sine of 2x, sine of 3x, etc. to get faster and faster oscillations. Okay, now if you take a reciprocal of the trigonometric functions, then you get cosecant, secant, and cotangent, which are the reciprocal trigonometric functions. So here are their graphs. So what you see over here is that the reciprocal graphs are right over there, okay? And the problem is that they are not defined wherever the corresponding trig function is 0. So for example, if sine happens to be 0 at a point, then cosecant is not defined, etc. So there are gaps in these functions which reflect the zeros of the underlying trigonometric function. But they are also somewhat similar to the trig functions in the sense that secant and cosecant have got a period of 2 pi, while the cotangent has got a period of pi. So these functions are quite useful in some parts of calculus. Okay, going a step further, we can now talk about the exponential functions, which are of the form a raised to power x. So now the exponent is variable. So for example, if you look at 2 to the power x, that's a case when the base a is greater than 1, then you have an exponential growth function. So here's the plot, and you can see it quite clearly that it is growing quite fast. On the other hand, if you take a number between 0 and 1, like 0.5, then you get a decreasing function. But in any case, these functions always pass through the point 0, 1, because e to the power 0 is 1, as you all know from your study of indices in algebra. So exponential functions are really useful for capturing growth on the one hand and decay on the other. So things like a population might grow exponentially and certain other things might decay exponentially, but together the exponential functions of different types give you a powerful way of expressing rates of growth or decay in calculus. So they are incredibly important and you should know them well. And finally, we'll talk about the logarithmic functions, which are defined as log x to the power to the base a, and they are the inverses of the exponential functions. So here's the graph of log x. Keep in mind that in the Wolfram language, the base is set to e, but if you want a different base, then you would say that over here, and you'd get back log x, but now to the base a quarter. And they are very similar in some sense to the exponential functions because they are in fact the inverses. So the logarithmic functions are quite useful, but as you can see, they grow much slower than the exponentials and they have their own uses. Okay, so we've talked about a fairly wide variety of elementary functions, and to summarize today's lesson, we have many different forms of functions and many different kinds of graphs studied today. So you could have linear functions, polynomial functions, rational functions, trig functions, etc. And together they are all that you require for studying calculus in this course for the most part. Okay, so we are basically done with today's lesson, and the next lesson will cover limits. So you'll really start doing calculus in this course next time. But before doing that, do look at today's lesson in the notebook that's supplied to you. Look at the accompanying exercise, go over them. You can only learn mathematics by doing, so spend some time reviewing, solving exercises, etc., and you should be in good shape to join me next time for lesson 4. So thank you very much. I hope you enjoyed today's lesson. I'll see you next time.